Good morning, guys. So this is our next unit, our new unit, work, power, and energy. We'll talk about how work is done, when work is done, what power is, and energy. The big idea here is the conservation of energy, and we'll talk about that too. But today, I just want us to talk about work, what work is, and when we say that work is done. So work in physics, work is done when an object moves through a displacement, when a force causes an object to move through a displacement. So work in physics is simply the product of a force multiplied by the displacement, right? The force multiplied by the displacement, that is the work done. If I carry something from this classroom, because I'm recording this from the class to the office, then the force that I'm carrying, which would be the force due to gravity, times the distance that I move it, is the work done. If Georgie pushes this block with a force of 8 newtons, pushes it through a displacement of, say, 10 meters, then the work done by Georgie is simply going to be that force times the displacement. For generalization, it's, and this will be 80. The units for work are joules. 8 is the force, so that's Newton. 10 is meter distance, so that's meters. So it's technically supposed to be Newton meter, but it was named the joule in favor of the scientists who discovered this relationship long ago. So a generalization of this formula can be, because right now we have work done is simply equal to force times distance, but a more general form of this formula is work done equals force times distance cosine of theta. Why am I saying cosine of theta? Is that we need to look at the component of the force that's causing the displacement. So if this, let me look at an example here. If the same Georgie was pulling the same block with the same force of 8 newtons, right, through the same distance of 10 meters, but this time his force 8 newtons is acting at an angle, because that's more convenient. It's more convenient to like pull something along the ground if you have a rope than having to bend. If that force was at an angle of say 30 degrees, then would need to consider, and the displacement is the same, it's still 10 meters, would still need to consider the force that's causing horizontal motion, right? The force that's causing horizontal motion. The force that's causing horizontal motion would be this horizontal component of the force, this horizontal component of the force right here, which is called force F cosine theta, because that's the force that's causing the motion. Displacement is still 10 meters. If there was friction, which there's always friction a lot of the time, if there's friction force, let's say coefficient of 0.4 friction, this thing has a mass of 5 kilograms, 15 kilograms. And then same question, how can we figure out the work done? Well, things are going to change now, because the force that's causing motion is now the net force, right? The net force. So we need to first figure out what the net force is, and then that net force times the displacement is what the work done will be equal to, right? So this is a more general way to state this equation, F net times distance. But this F net in this situation is going to be F cos theta, F cosine theta minus the force of friction, right? I'm using small f, times the distance. So F cosine theta is just 8 times cosine 30 minus friction force is mu times normal force, right? What just happened? Mu times normal force. My projector went out and did not come back. Let me first fix the projector issue. We're back. So mu times normal force, the normal force, I need to figure out what that is, then multiply this answer by the distance, which is 10 meters. So in this situation, the normal force is supposed to be this Fn, right? But I have a force of gravity going downwards, but I have another force the vertical component of this force, that's going to be 8 sine theta, 8 sine 30. So the normal force, if you look at it carefully, the normal force is uh, Fg minus 8 sine 30, right? I hope you see that. So when I'm calculating my work done, it's going to be equal to 8 cosine 30 minus mu, which is 0.4, times normal force, which is Fg, mass times gravity, which is 15, times 9.8, multiply that by, subtract, not multiply. Right, this again, my net force, set down here, 8 cosine 30 minus 0.4 times the normal force is mass times gravity, 15 times 9.8 minus 8 sine 30. All of that multiplied by 10 is going to be the work done. So the general equation for work done, the only reason for this example is that we have to consider the net force, right? The net force multiplied by the distance the displacement that net force causes the object to move. Let's look at this example. Very zoomed in example. How much work is done on the lawnmower by the person if he exerts a constant force of 75 at an angle of 35 below the horizontal and pushes the mower 25 meters on a level ground? Now remember, work done is equal to Fd cosine theta, right? The component of the force that does the work is going to be F cosine theta. Multiply that by the distance is Fd cosine theta. Because the net work done is equal to force times the displacement, right? But this force is the component of the force times the displacement, the net force. So it's supposed to be net force, but in this case, the net force, because the only force that's acting is the forward force that's pushing this object, and that component is F cosine theta times displacement. So the force is 75 times cosine theta, which the angle is 35, times the displacement, which is 25, and that gives you the answer. Now, I'm going to need you to fill out pages 90 to 91 of your workbook, right? But before you go there, we need to talk about the relationship between work done and energy, right? Work done and energy. Before we even go there, let's just talk a little bit about power. I use this example a lot. If I ask Georgie to carry 10 kilograms of something or 50 kilograms of something, or a more relatable example, if I ask Georgie to bench press 50 kgs, right, 10 reps, and it takes him 3 minutes, right? So Georgie takes 3 minutes to bench press 50 kgs for 10 reps, right? And then you ask Senai, and Senai only takes 1.4 minutes to bench press the same 50 kgs for 10 reps, right? I think you can, just from this, you can clearly see that Senai has more power than Georgie, right? Senai has more power than Georgie. But why? They are both doing the same amount of work because they are doing, they're doing 50 kgs for 10 reps, right? Or both of them are doing 50 kgs for 10 reps, but Senai is doing it faster. Since Senai is doing it faster, we can say Senai has higher power. And power in this sense is the rate at which work is done. How fast you do your work is how much power that you have. So power is simply the rate at which work is done. At which work is done, or the rate at which energy is transferred. Energy is transferred. One other thing that I didn't talk about work, just to emphasize, work is F net times the displacement. Now, this is very important because if you don't have a displacement, not just distance, if you don't have a displacement, you do not have work done. If you run 5 laps around the field, you start at the same place and then you finish at the same place, since your displacement is 0, your work done is going to be 0. And also just a quick thing, if we look at a graph of force, if I draw a graph of force against displacement, right, the area under that graph, the area under this graph of force versus displacement will give you the work done. And if the area gives you the work done, because you can see area will be length, right, which is displacement times time, which is force, times height, which is force, and that's work done. So what does the slope of that graph represent? That's a question I'm leaving up to you. What does the slope of that graph represent? All right, so pages 90 to 91 of your workbook, the very first question you have there is actually related to what I was starting to talk about, the graph of force versus displacement, right? Graph of force versus displacement. So we have a graph there, force versus displacement, and there's a claim. The cat will have a change in mechanical energy of 48 joules as its displacement is changed by 12 meters. Before we go to mechanical energy, one last thing about work. Sorry, guys. Every time work is done, right? Every time work is done, there is a change in energy, right? There's a change in energy of the object. Energy is transferred when work is done, right? Energy is transferred. If Sanai is bench pressing, he's transferring energy from his muscles onto that mass that he's pushing. If I'm pulling a table and it's making a sound, which you guys can hear, as I'm pulling the table, my energy the work that I'm doing to pull the table is transferred into energy. One of those energies is energy in motion, which you know is kinetic energy. The other energy is sound. The other energy is friction. And we'll talk about this a little bit more when we talk about conservation of energy. But like I said, one of the energies transferred is motion, right? My work done is converted to motion. The work that I do on pulling the table is converted to motion. It's converted to sound. It's converted to heat because there is friction as the table is sliding across the ground. So energy in motion is simply known as kinetic energy. Sound energy is still the same thing as sound energy. Heat is present because of friction. So this work that I have done on this object is leading to energy being transferred. So work done is the same as energy transferred. And the units for work done and the units for energy are exactly the same thing, right? Same units for work and same units for energy. Here when we talked about power as the rate at which energy is transferred, I'm just going back because I didn't write the units. So power would be work done because it's a transfer of energy divided by time, right? Power is work done divided by time. And since power is work done divided by time, power is also force times displacement, net force, times displacement divided by time. But you know that displacement divided by time is the same thing as velocity. So power can also be written as F net times V. The units for power are watts. Watts. If you want to play a joke on your friends, you can ask them the question. Actually, it's not even a question. Just say, what is the unit for power? Right? Just say that sentence to any random person and then see them struggle. Yeah. So what is the unit for power? Then you see them go, joules, something. Anyways, so when work is done, energy is transferred. Some of that energy is kinetic energy, right? And some of that energy is potential energy. when Sena is bench pressing, because the object is not moving horizontally, it's moving against gravity, right? The force that he's experiencing is the force of gravity. That work he's doing is against the gravitational force of that mass, so it's potential energy that's transferred, right? But when I am pulling the table, then the energy that is transferred to the table is kinetic energy, because the table goes into motion. So why am I saying all of this? Is just so we are able to figure out pages 90 and 91. Kinetic energy, energy in motion, is the same thing as half times mass times velocity squared. You should have found this somewhere in your earlier physics courses. The units are still joules, and potential energy is mass times gravity times height. We will talk about this more on Monday, and still limits with joules. What I want us to focus today is the energy in motion, and that's kinetic energy. So in this object, in this case, part A, there's a claim that the cat will have a change in mechanical energy of 45 joules as its displacement is changed. Is that claim true? As its displacement is changed by 12 meters, is it true that it will have a change in mechanical energy of 48 joules? So mechanical energy is the same thing as kinetic energy plus potential energy, right? In this case, since we only have kinetic energy, so all the mechanical energy of this system is its kinetic energy. So is it true that the energy will change by 48 joules? What do we know? We know that when work is done, energy is transferred, right? Energy is transferred. So the work done to move this object is going to be equal to the kinetic energy that it gains. So therefore, from 0 to 12, the kinetic energy gained from 0 to 12 is supposed to be equal to the area under that graph, because the area under that graph from 0 to 12 is the work done from 0 to 12. So if I calculate this area, it's just a rectangle, and its length times width. So that area is 4 times 12, which turns out to be 48 joules. Since the work done from 0 to 12 is 48, it is true that this claim is true that the change in mechanical energy is 48 joules. So I've calculated the area by taking a force of 4 newtons times a distance of 12 meters to get 48 joules, right? This area is also known as the work done on the object. Fill in the blanks. The claim makes sense because the work done on the object is equal to the change in the mechanical energy or in the kinetic energy of the cut, right? Is equal to the change in the kinetic energy of the cut or the mechanical energy of the cut. Explain how the graph above could be used to determine the final speed of the cut after 12 meters. Now we've said, or we know, that when work is done, it leads to a change in kinetic energy, right? Work done leads to change in kinetic energy. The work done has been 48 joules. Kinetic energy is the same as half times mass times velocity squared. So I can just use this equation. I know the mass of the object is 1, and the only unknown in this equation is v. So you can go ahead and calculate for v. Now, that's how you get the speed, but the question asks you to explain. So in words, how would you explain that? That's the task that you have. Second part, part C. On the grid, sketch a graph of the acceleration of the cut as a function of displacement from x equals 0 to x equals 12. Now, in the previous graph, I saw that from x is 0 to 12, there was a force of 4 newtons acting on this object, right? The force of 4 newtons. I know that force is equal to mass times acceleration. Since the force is 4 newtons for those first 12 meters, and I know the mass of the object, I can calculate the acceleration and see that the acceleration is 4 meters per second over the first 12 meters. And that acceleration is constant over those 12 meters as 4 meters per second. So my graph, that's not my graph, my graph is going to be an acceleration of 4 meters per second, which is constant for the first 12 meters. This is a straight line, let's not draw it straight. That's my acceleration graph. All right, after creating a graph of acceleration versus displacement, Angela says, oh, the slope of a VT graph represents acceleration, which is correct. Slope of a VT graph, right? Slope of a VT graph represents acceleration. So since the acceleration is constant and is meters per second, right, and is 4 meters per second squared, the velocity should be a line with a slope of 4 meters per second. Do you think Angela is correct? Angela is basically saying that since the graph, since the slope of a VT graph, because you know the slope of a VT graph, and this is the trick in this question, the slope of a VT graph is acceleration. That is true, right? But first of all, this graph is not an AT graph. It's an acceleration versus displacement graph, right? It's not an acceleration versus time graph. This acceleration changes with time. I mean, the speed of the object changes with time, but the acceleration of this object is not changing over the 12-meter displacement. So Angela is not correct, unfortunately. Angela is not right, right? Angela is not right because this is not a graph of acceleration versus time. It's a graph of acceleration versus displacement, right? If it was a graph of acceleration versus time, you would see a non-uniform acceleration over those 12-meter, that 12-meter interval, because this force is acting for the whole 12 meters. Like the force is not pushed on then released. No, the force is acting for the full 12 meters, and for each second that the force is acting, the acceleration of the object is increasing. Does that make sense? I hope that makes sense. And I hope you can work out something from what I've said to explain this. But we'll talk about it again on Monday if it's still confusing you. All right, sketch a graph of velocity of the cart as a function of displacement. Now, remember, I know that velocity is the same thing. Velocity can be got from this expression that work done is the change in kinetic energy. So the work done is half times mass times velocity squared, right? So if I go back to this graph, the initial graph that I started with, I can calculate the velocity at different points. I can calculate the velocity at 2 meters, because at 2 meters, the work done will be 2 times 4, which is 8, right? So I can use this 8 in this expression. I can use the 8. So I'm going to have work done, and then if I try to make V the subject in this equation, V will be 2 times work done divided by mass square root. So V is equal to 2 work done divided by mass square root of that. So at 2 meters, I have displacement. At 2 meters, the work done is 8. At 4 meters, the work done is 4 times 4, 16, right? 4 times 4 is 16. At 6 meters, the work done is 24 because it's times 4, the force is the same. At 8 meters, the work done is 32. At 10 meters, the work done is 40. And at 12 meters, the work done is 48. So I can use this equation, 2 times work done divided by mass square root. Since the mass is 1, it's just 2 times work done. So 2 times 16 is, 2 times 8 is 16, square root of that is 4. 2 times 16 is 32, square root of that is like 5.8. That's a guess. You guys get the actual number. 2 times 24 is 48, square root of that is maybe 6.9. 2 times 32 is 64, square root of that is 8. So using these points, I can plot a graph of displacement, velocity versus displacement. When the displacement is 2, the velocity is 4. So that's over there. When the displacement is 4, the velocity is 5.8. When the displacement is 6, the velocity is 6.9. Oh, 6.9. When the displacement is 8, the velocity is also 8. 8 to 8. When the displacement is 10, you can get the answer. And then you'll have a graph that's kind of looking like this. That will be your graph of velocity versus displacement. I hope you can see that it's very different from a velocity time graph, right? Right? It's kind of different from a velocity time graph. So, quantitative analysis. This equation can be used to describe the velocity of an object with constant acceleration as a function of position. Is this equation consistent with the graph you sketched? Let's see. In this equation, v1 squared equals v0 squared, but v0 is 0 because it was at rest, times 2 times acceleration times delta x, right? If I try to graph this equation, for v, if I make v the subject, I have v is equal to square root of 2a delta x, right? And since you guys are doing pre-calc, you know that the graph of a square root function looks something like that, which is a very similar shape to the graph that we have here, square root function. So I can conclude that yes, this equation is consistent with the graph I sketched, because the graph of a square root, it's the same shape as the graph of the square root function, which is consistent with this equation, because from this equation, v1 is equal to square root of 2a delta x. Sorry this came late, but I hope you can use this to finish pages 90 to 91, and I'm going to assign you, no, I won't give you any homework. Yeah, all right.